Hello everyone, in this video we are going to discuss AVL trees, which are a type of self-balancing binary search tree. We will first understand the need for AVL trees, then learn about height balance factor and finally study the 4 rotation causes used to balance an unbalanced tree. This lesson is especially useful for data structures and algorithms, students and exam preparations. Before we continue, if you find this video helpful, please like the video, subscribe to the channel and turn on the bell icon so you won't miss our future lessons on data structures and algorithms. We are talking about binary search tree here. So a special type of this is the AVL tree. We use some values like this here. Let's see how these values are displayed in a binary search tree. Then we know how to insert this. First you can insert 14, then you can show the axis in a node like this. Then you need to insert 16, 14 comes after comparing. 16 come to the right, then you insert 20, then you insert 15, 10 and 17. Here are the steps to take in a binary search tree like this. Then there is no problem with this. Let's see what happens if we insert these elements in a different order. Then I will give some data like this. This is the same data as before, but the order is different. So let's see how it comes out if we show this is as the binary search tree. First, we insert 10, then 20, 13, 14, 15, 16 and 17. Then we can see that the binary tree is formed like this. Why do these two changes like this? Actually, one changes according to the order we give first. The problem with this is that we are searching for a value from this. Imagine that the value 16 is searched for both these causes. Then if we search for the value 16 in the first case, you will have to do this after 2 comparisons. It with 14 then is not equal, so it goes to the right hand side. Then with 16 we can identify 16 in this way. In binary search, looking at the case on the right, you can see that the value 16 is found after 6 comparisons. So this is the difference in performance between the two causes if you can search for the value in a fewer steps. Then would be great. In this case on the right, we can identify the value 16 after 6 comparisons. However, the one of the left is an AVL tree, but the one of the right is not an AVL tree. So, for a tree to be an AVL tree or balanced tree, there is an important condition that must be satisfied. That condition is if you consider any node and take the height of its left subtree and the right subtree. The difference between those two heights must be less than or equal to 1. That is why it is shown here in this pair. So the difference must be either 0 or 1. Let us understand this using an example. Consider the following tree. Now if we look at node 14, the subtree on the left side of the node 14 in this, and the subtree on the right side of node 14 is this. Now we can see that for node 14, what is the height of the left subtree? If you count how many steps we need to go from node 14 down to the lowest leaf node, we need 2 steps like this, so the height of the left subtree of node 14 is 2. Next, what is the height of the right subtree of node 14? In this case, we need to go only 1 step to reach a leaf node. So the height of this right subtree is 1. Therefore, the left height is 2 and the right height is 1. What is the difference between them? The difference is 1. We can represent this as 1 like this. This difference between the heights of the two subscribes is called the balance factor. So here the balance factor is 1. Next, let us look at the node 20. If we consider node 20, its left subscribe height is 1. Because there is only one element and we need just one step to reach the leaf node. Similarly, the right subscribe height is also 1. So, the difference between them is 0 and we can represent it like this. Also, if we consider leaf node, its balance factor is also 0. So, we can represent leaf node in this way. Now, if we take this entire trees, we can see that every node has a balance factor of either 0 or 1. Therefore, we can identify this tree as an AVL tree. If the balance factor becomes greater than 1, then that tree is not an AVL tree. Now, let us check whether the binary search tree we considered earlier are AVL trees or not. First, if we take the left side tree and check the balance factor of each node, we can see that every balance factor is 0. So, that tree is completely an AVL tree with no issues. Next, if we take the right side case, the balance factor of the nodes can be observed like this. Let us look at one example. Consider the node 20. For node 20, there is no left subscript, so its left height is 0. If we look at the right subscript, the height is 5. So, the balance factor here is 5, which is why 5 is written here. As you know, for a tree to be an AVL tree, the balance factor must be 0 or 1. So, when we look at all the nodes, we can clearly see that these nodes have problems. Because such a node exists, the binary search tree is not a balanced binary search tree. Or in other words, is not a AVL tree. Now, you should have a clear understanding for how to identify an AVL tree and non-AVL tree. So, the next step is when we find an unbalanced tree, how do we convert it into a balanced tree? We can do this using 4 different conditions. There are the 4 conditions that you can identify in this way. Now, let us understand this using a small example. Basically, when we find a tree that is not an AVL tree, we convert it into an AVL tree by using rotations. For example, let us take their values 10, 20 and 30. As we know, using these 3 values, we can construct 6 different binary search trees because the insertion order can be changed. First case, first we insert 20, then we insert 10 to the left of 20. After that we insert 30. When we check the balance factor after inserting 13, we can see that all balance factors are 0. There is no issue there. So, this tree is a balanced binary tree, or in other words an AVL tree. Second case. Now consider the second case. First we insert 20, then we insert 13, after that we insert 10. When we check with the balance factor on this tree, all of them are also 0. So even in the second case, the balance is a balanced binary tree, that is an AVL tree. Third case. Now let us move on to the third case. So far we have not encountered any problem condition. In this third case, first we insert 10, then we insert 20, which go into the right of 10. At the point the balance factors on the nodes are 1 and 0. Next we insert 13. Since 13 is the greater than 10, is going to the right of 10, and the since is also greater than 20, is the goes to the right of 20. Now when we check the balance factors, we can see that one balance factor is greater than 1. This means that a tree is not an AVL tree. Fixed in the third case, right and right condition. Let us now see how to fix this convert into the AVL tree. The balance becomes unbalanced after inserting 13 from the root node 10. Then insertion path is right. So this is the right condition. For a right condition, we perform a left rotations. Fourth case. Now let us move to the fourth case. First we insert 13, then we insert 20, then we insert 10. When we check the balance factor, we can see that one node has a balance factor greater than 1. So this tree is not an AVL tree. This is a left condition because 10 is 1 on the left, 20 is 1 on the left of the root node. For left condition, we perform the right rotation around node 13. After rotation, we get a balanced tree like this, which is now an AVL tree. Fifth case. Now let us move on the fifth case. First we insert 10, then we insert 13, then we insert 20. Here, when we check the balance factor, we can see a value for 2, so the tree is unbalanced. The tree becomes unbalanced after inserting 20. From the root node, we go to right node 10, then left from 13. So this is a right-left condition. This case requires 2 steps. Step 1, perform a right rotation around node 13. Node 20 moves up. Node 30 moves down. Step 2, performs a like rotation around node 10. Node 10 moves down. Node 20 moves up. Node 13 also moves up. After these 2 steps, there becomes a balanced AVL trees. Sixth case, now we let us move to this sixth case. First we insert 13, then we insert 10, then we insert 20. When we check the balance factor, we again get a value of the 2, so this is not a AVL tree. The tree becomes unbalanced after inserting 20. From node 13, the insertion path is left to 10. Then right to 20. So this is a left-right condition. This also requires 2 rotations. Step 1, perform a left rotation around node 10. Node 10 moves down. Node 20 moves up. Step 2, since there is now a left situation, performs a right rotation around node 13. Node 13 moves down. Now 20 moves up. Now 10 also moves up. After this rotation, we obtain a balanced AVL tree. These 4 conditions RR, LR, RL are the ones used to balance an unbalanced binary search tree and convert into an AVL tree. Now let us look at the one complete example by combining everything we have learned so far. For this example, I am using the following set of elements and the order of insertion is shown here. First, we insert 13, then we insert 25, after that we insert 35. Since 35 is greater than 13, it is inserted on the right side. When we check the balance factor at this point, they all come out as 1, so this is no issue. Now let us insert 20. The value 20 is insertion in this way. When we check the balance factor, now we see only 1 and 0 and 1. So there is still no problem. Next, when we insert 15, the balance factor becomes 2. So now this tree is no longer balanced binary search tree. We can see that 2 nodes have become unbalanced. If you look at the lowest unbalanced node and trace the path of the newly insert value 50, we can see left condition. That means we need to perform a right rotation around this unbalanced node. When we rotate, node 25 moves down. Now 20 moves up, now 15 also moves up. After this rotation, we get a tree like this. Now there are no issues and the balance factor becomes 0 and 1. So the tree is now an AVL tree. Next, we insert 5. After inserting 5, the tree again becomes unbalanced. This imbalance occurred because of inserting 5. If we trace the path from the unbalanced node to 5, we get left, left, left. So this again in left, left condition. As we know, when there is a left, left condition, we perform a right rotation. Then rotating around now 13, now node 13 moves down, now node 35 moves further down, now node 20 moves up. When node 20 moves up, node 25 becomes the left child of 30. This gives us a tree like this. Now let us move to the next process and insert 10. After inserting 10, we can see that one node becomes unbalanced. Now let us check the path from the unbalanced node to the newly inserted value. Here, we observe a left-right condition. When a left-right condition occurs, we must perform 2 rotations. Step 1, first we perform a left rotation around node 5. After this step, we get a binary search tree like this. Step 2, next we perform right rotation around node 15. Node 15 moves down. Node 10 moves up, node 5 also moves up. After this rotation, we obtain a tree like this. When we check the balance factor, now they all become 0, so this is an AVL tree. Now let us insert 15. There is no problem here, and the balance factor remains 0 and 1. So the tree is still a AVL tree. After that, we insert 16. When we insert 16, we can see that tree nodes become unbalanced. Let us look at the lowest unbalanced node. The imbalance occurred because of the inserting 16. To reach 16, we follow a right path, so this is a right condition. If a right condition, we perform a left rotation around the unbalanced node. When we rotate, node 25 moves down, node 15 moves up, node 16 also moves up. After this rotation, we get a tree like this. Now the tree is balanced again. So through this video, you should have gained a good understanding of AVL trees. We will meet again very soon with another video. Thank you.